The topic of this video is wavefunction normalization. Previously, we discussed what the wavefunction was, and we had a small primer or reminder on probability. We're going to take that to the next step and discuss how the wavefunction behaves like probability density. So the first thing we'll talk about is normalizing the wavefunction. After that, we'll discuss how there's a time invariance for the normalization, so that the normalization, once you do it for one time, it doesn't matter how the wave function evolves with time, it will be normalized for all time. So we have all the discussion that we had before on probability for discrete sets. We can now extend all those statistical quantities to a system of continuous variables. So here I'm going to look side by side and show the two different aspects. So on the one side, we introduce, instead of P of J like we had before, we introduce the probability density, leaving out the time dependence for the moment, as rho of X, which is psi modulus squared. So in our discrete system, we have P of J is equal to N of J over N. That's the probability of finding the number J in a discrete distribution. For a wave function, that probability is just rho of X, which is the probability density from the wave function. Remember also how the probabilities had to add up to 1, because if you sum all these as a function summing of J, you divide by N, the sum of N of J is going to be N. And so this has to be equal to 1. So the probability of finding some value throughout the entire distribution has to be 1. Similarly, the probability density for a wave function in quantum mechanics has also to be 1. But instead, we have continuous variables. So 1 then is equal to the integral from minus infinity to infinity of rho of X dx. So that has the same correspondence to the sum of the probabilities. Finally, the expectation value f of j, which was the sum over j of f of j times p of j, is now in the continuous variables going to be very similar. You have f of x, and the expectation value of f of x is the integral from minus infinity to infinity of f of x times rho of x integrated over x dx. And finally, the variance, sigma squared, which we calculated in the last video, which was the expectation value of delta j quantity squared, or equivalent to j squared, the expectation value of j squared, minus the expectation value of j quantity squared. And that now in a continuous variables becomes, well, it's still called sigma squared, but it's really just the expectation value of delta x. And similarly to here, you have the expectation value of x squared minus the expectation value of x quantity squared. So with these, we can now formulate quantum mechanics and how the wave function behaves in the same way as probability theory. So our goal then is to normalize the wave equation. Now, besides satisfying the Schrödinger equation, the wave function also has to have one other important aspect. Since we're describing physical systems, it must have some physical significance. So recalling that the Schrödinger equation was given by this IH bar partial psi with respect to t equals minus h bar squared over 2m partial squared psi with respect to x squared plus v times psi. Well, if you want to believe that the statistical interpretation works, which we believe it does because it does reproduce all experimental data, then the wave function has to be normalized in just the way that we saw in the previous slide. That is, if you integrate the probability density over all space, you must get 1 because the system has to be somewhere in space. And so that gives us an integral of the probability density, which is just psi modulus squared, modulus of psi squared, integrated from minus infinity to infinity dx equals 1. So this is a property that we must have whenever we have a physical wave function. If we can't normalize the wave function, it can't represent anything physical. So the question then is, there's a variable t here. We talked about before we had rho of x, but we didn't have a time dependence. But the wave function has a time dependence. And if we integrate over x, we still have a time dependence. So the question is this normalization constant? So if we normalize at t equals 0, what guarantees that that wave function will remain normalized over all times? Well, we're going to use the properties of the wave function, that is, that it satisfies the Schrodinger equation, to help solve that. So we can start by looking at the normalization integral and take the time derivative of that normalization integral. So on the left side, on the right side, we're going to take that time derivative and then calculate, using the Schrodinger equation, reinterpret that and see if we get a constant. So we're going to take d by dt of the integral from minus infinity to infinity of psi of x and t modulus quantity squared dx. Well, that's easy enough. We can bring that the full derivative d by dt into the integral. Once you bring it into the integral, it becomes a partial derivative. So now it's a partial derivative with respect to t of the modulus squared of psi, a dx integrated. If we now look at this integrand closely and apply the product rule, we can see what happens. So let's imagine schematically this is d by partial with respect to time of psi squared, and I've dropped the variables just to make it a little bit more compact, is equal to partial with respect to t of psi star psi, because the modulus is simply the complex conjugate times the function itself. That's all the modulus squared is. And so I can now apply this time derivative to this product. Using the product rule, we get that we have psi star times partial of psi with respect to t plus partial of psi star with respect to t times psi. And now, if we look at the Schrodinger equation, we realize that this part here, the partial of psi with respect to t, is simply what's on the left side, and here in red. And so, we also look at this one, and we see that the complex conjugate, the partial with respect to time of the complex conjugate, is simply what's on the left side if we take the complex conjugate of the whole Schrodinger equation. So if we look here, we have partial psi with respect to t, that becomes partial psi star with respect to t. On this side, we have I h bar over 2m, partial squared with respect to x squared. And this gives you, when you take the complex conjugate, you get minus I h bar over 2m, partial squared of psi star with respect to x squared. And then the third term is minus I h bar v psi. And if we take the complex conjugate of that, we get I h bar, or over h bar, v times psi star. Now, this doesn't look exactly like the Schrodinger equation before, but we had to get rid of the constants in front of here. So it's I h bar, and when we divide by I h bar, this turns into, the positive signs go away. This flips a sign, and this gives you an I over h bar. So, if we now make that substitution into these two terms, we can clearly substitute this term and this term, but you'll notice that these two terms cancel. If we put them in here, they're going to cancel out. So we can ignore these two terms because they'll cancel out exactly. So we're left with only the terms in red and green. So we have psi star times I h bar over 2m, partial squared with respect to psi, partial squared of psi with respect to x squared, minus I h bar over 2m, partial squared of psi star over, with respect to x squared, of psi. Pardon me. If we look at this, we can factor out the IH bar over 2m for both of these, and we get psi star partial squared, second partial of psi with respect to x squared, minus second partial of psi star with respect to x squared psi. If we now add and subtract this term, which is partial psi with respect to x times partial psi star with respect to x, we can factor this term in here. So we now bring this down from the top, so it's partial with respect to time of the modulus squared of psi is equal to IH bar over 2m times the quantity in parentheses, which has partial psi with respect to x, partial psi star with respect to x, plus psi star times partial squared with respect of psi with respect to x squared, minus partial squared psi star with respect to x squared psi, minus partial psi partial x times partial psi star partial x. So these two terms are just added and subtracted, but now I can regroup this. So if I regroup this, I realize that this is simply the partial with respect to x of IH bar over 2m times psi star partial with respect to psi partial of psi with respect to x minus partial of psi star with respect to x times psi. And you can see how this works, because if I take the partial derivative here, I take partial derivative using the product rule. Here I get two terms. One is the first term, and then the second term is this one. And if I take the partial with respect to x of this term here, this product, then I'm going to get this term and this term. So if we now put this integrand back into the original expression, we realize that, so we have d by dt of partial of psi modulus psi squared integrated dx becomes the partial with respect to t inside the integral, but we just find out that that becomes exactly the integral from minus infinity to infinity of the partial with respect to x of IH bar over 2m times this quantity here, psi star partial psi with respect to x minus partial psi star with respect to x times psi integrated times dx integrated over x. But if you look at this, this is now a perfect derivative. And so the integral and this derivative sort of cancel each other out, and we're left with the whatever else is in there, which is IH bar over 2m times this quantity in parentheses, which is psi star partial psi with respect to x minus partial psi star with respect to x psi, evaluated at minus infinity and plus infinity. Now, this must vanish if the wave function is well behaved and approaches 0 at plus or minus infinity. And I haven't made a proof of this, but it's clear if you want a physically significant wave function, it cannot go to infinity and infinity, because otherwise you cannot integrate it. It can't even go to a constant value at infinity. Otherwise, it can't be normalized, because its integral over infinity, from minus infinity to infinity, is infinite. So the only physically significant, that is normalizable functions, are ones that approach 0 at plus or minus infinity. In that case, then this product here, or these terms here, must go to 0, because psi star will go to 0 at infinity and minus infinity, and psi will go to 0 at plus infinity and minus infinity. But even better than that, the derivatives actually go to 0 for well-behaved physical functions. So all these terms go to 0 at the endpoints. So because of that, now this quantity is exactly 0. Now if you go back and look at what we started with the time derivative of the normalization integral. And that means that if the time derivative of the normalization integral is 0, then the normalization integral is a constant. And if it's equal to 1, the function will remain normalized for all time.